Hello everyone. Let's make something simple because it's the beginning of July and I'd rather relax than program overly complex shaders. So we'll create a simple image warp effect that fits into a single line of code. So let's go ahead and program that to one line. So let's follow the usual pattern and create a new scene with the usual image in the background, that is, a screenshot from our game Whispers of Prague. Let's do all the preparatory work. So I am creating right-click the scenes folder and create a new scene, which is a 2D scene, and let's call it, I don't know, one line warp. Okay, and I'll find the mentioned screenshot found in JPEG and drag it into the 2D editor. So the Sprite 2D node was automatically created, and in the inspector, let's do the usual stuff, canceling offset centered, and transform position, let's reset to 0, 0. Okay, and scrolling down to the material section where I create the usual new shader material, click it and create a new shader, which is type shader mode canvas item and the name one line warp GD shader, and I'll put it to the shaders folder and create and click it again to open it in the shader editor. Okay, and as always, I'll delete everything from the generated code that we won't need for our effect, leaving only the fragment function, deleting vertex and deleting the commented out light, Ctrl S to save. Okay, and we can start writing the code. As I said at the beginning of the video, it will be a single line inside the fragment function. So I'll write its basic version first and then we'll keep improving it. And the line would be the usual color equals the function texture applied on the texture, our background image, and the standard UV coordinates. Okay, so of course we don't see any changes because the code does exactly what an empty shader would do. It reads the pixel value at the current coordinates and renders it at the same coordinates. So let's see what happens if we divide these coordinates by their dot product. So here instead of UV I will use divided by dot of UV and UV. And let's show the whole image. Okay, so now it looks more interesting. Sure, the image has rotated and we are only seeing part of it, but some curvature can be has been introduced, so we are on the right track. Okay, what exactly is the dot product? It's a fast alternative to calculating the distance between two vectors because, by definition, it's essentially the squared distance, and as a result, the amount of curvature changes according to the pixel's distance from the origin, which is located here in the top left corner of the image. So let's keep improving it. We want the effect to be symmetrical, with the warp changing from the center rather than from the top left corner. In my other shadows, I usually create a new variable and assign it a UV minus 0.5 value. In this case, to keep everything on a single line, we'll perform the subtraction directly inside the dot function. So as I said, let's subtract 0.5 from both arguments of the dot product function. So UV minus 0.5 and the second UV minus 0.5. Okay, so now we can see the entire image, and if we zoom the camera in, it becomes clear that it's no longer rotated. However, we'll get a better effect if we subtract the dot product from 1. because dividing by a smaller number produces a larger result, giving us the curvature we are after, like this. So where it is dot, so I will just put it to the brackets and add 1 here, 1 minus dot product. Okay, wait. Very well, we are almost done. We just need to fine-tune the coordinate offset so the effect is perfectly symmetrical. First, I'll subtract 0.5 from these UV coordinates and as well. Be careful with the parentheses. They are very important. So I mean here in the UV I will do open brackets and minus 0.5 and end brackets. All right. And finally, since the result is offset by half, let's add 0.5 to the start of it. 0.5 plus this. Very well. I would say the basic effect is now complete. Notice that this time we ended up with an ellipse instead of the usual circle, because we are not compensating for the aspect ratio. That simply wouldn't fit onto a single line of code. We can work around that by making the element square. For example, if we wanted to simulate a peephole in a door, something like this. But of course, let's get back to the usual rectangle. Okay, so it would certainly be useful if we could control the amount of warp with a parameter. So first I will add a uniform parameter. So let's put it right here, a uniform float warp with a hint range, and the initial value I'll set to 5, and the range will go from 0 to, let's say, 100, and I think the step can remain 0.1. By the way, we are still sticking to a single line of code. Parameters don't count. Now we'll multiply the dot product in our calculation by this parameter. So here 1 minus dot, so 1 minus warp times dot. Okay. And I think we can try it out in the inspector, shader parameters. Let's increase the warp. All right, this is very, very interesting. And here it is cancelled out when it's 0. Okay, you have probably noticed that artifacts start appearing in the corners of the image because higher values of the warp parameter cause this calculation to produce negative numbers. We can prevent that by wrapping the entire formula in the square root function, like this. So here in the front of these brackets, let's use sqrt. All right, and now if I change the parameter again, we can see that it's perfectly fixed. Okay, as we know, the square root function is undefined for negative numbers, so the Godot shading language uses 0 instead, which results in black. Other GLSL implementations might behave differently, so in those cases it would probably be enough to clamp the lower bound of the dot product using the min function and an appropriate threshold value. But in our case, that's not necessary. The final improvement we'll make to our code is to replace the 0.5 constants here, here, and here, and here. 0.5 constants with parameters. Here we need to distinguish between the offset of the UV coordinates, and which I'll call center, and the offset of the final image, which I'll call shift. Both parameters will be vectors so that we can manipulate the image along both axes. So let's add the parameters here to the parameters section, uniform vec2 shift, and the initial value would be vec2 0.5, and let's do the same for the center. Uniform vec2 center equals vec2 0.5. Okay, all that's left is to use them in the code, which I'll modify into this form. So first, let's replace this one with Shift. Okay, and now I will copy center and paste it here at the other occurrences of the 0.5 constant here, and here. Okay, and now when I change the shift parameter, we can see the resulting effect. Looks like if it's moving across a curved surface. And why? Okay, I would say it's pretty cool. And changing the center parameter, on the other hand, can be used for vertical or horizontal panning. All right, and yeah, that's everything. Thank you very much for watching. We ended up writing a very short piece of code that could be useful for various visual effects, scene transitions, and similar applications. Moreover, you can also experiment with the algorithm itself by replacing the square root function with something else. I tried x and 10h, for example, which produced different looking distortions, and some of the combinations turned out to be quite interesting. Of course, everyone can experiment and see what works best. For now, take care, good luck with your game projects, and I'll see you in the next video.